All right, it is 1 p.m. We are live, got the audio and the video running, and the lecture slides are up. So welcome back to Statics. We're on lecture 15. We are rocking and rolling. A couple of quick announcements. I got the attendance grades up to date, and we're going to keep on with the same homework schedule. We're well into our body of topics, in the second exam territory on rigid bodies. Last time what we did is we introduced the concept of a moment. And a moment is technically defined as the cross product that I have here on the board. I'm going to turn the slides off here in a second because I want to do something with this definition. What we're going to do today is we're going to take what we did on Friday, which was a generic expression for a moment in 3 dimensions, and we're going to simplify that to moments in 2 dimensions because they get a lot easier, a lot more manageable, and I think you can glean a little bit of conceptual understanding about what a moment is in 2 dimensions as well. So, but before we do that, let's recap what we've done so far. So the first thing is to recap the cross product. Just making sure that we're all comfortable with that. We are going to do some stuff with cross products today, although there will be some workarounds, but that'll become clear here in a second. So what is a cross product? We have vector 1, vector 2, or vector A, vector B, whatever you want to call it. And I want to define a new vector, A cross B, such that A cross B points normal to the plane, according to the right-hand rule. And that the magnitude of that vector is equal to the parallelogram formed by those 2 vectors. Long story short, we can compute the cross product using the determinant of a 3x3 matrix that's set up with the top row being ijk, the middle row being the coefficients of your first vector, and the lower row being the coefficients of your second vector. As for actually grunting out the coefficient or the cross product and the determinant, there are a couple ways of doing that. You could just plug it into your calculator; it'll do it for you. But doing it by hand, there's either the rule of Saris, which you see here on the left, or cofactor expansion. I don't really care which one that you use, although today I'm using cofactor expansion because I want to simplify moments in 2D, and it's actually kind of easier to see how that works with cofactor expansion, and so that'll become clear here in a bit. Where do cross products come into play in statics? Well, the formal definition of a moment is R cross F. Okay, so let's just make sure that we are aware of this. So if we have a point out in space, and we have a force that is not going through that point, then it generates what we call a moment about that point. Okay, and so generally that moment is defined as force times distance, and from a mathematics perspective and a vector perspective, we define that as R cross F. So F is your force vector, and R is what's called the position vector. The position vector starts at your point of interest, so you've got your force, and here's your point about which moments are being taken. So it starts at the point of interest, and it ends at any point along the line of action of F. Because remember, it goes off that parallelogram principle. The idea is that the area of that parallelogram doesn't change as long as R starts at the point of interest and points to the line of action. Now, again, ultimately, what we really care about is the magnitude of that moment, which is just force times distance. And the term distance, I'm using the term distance. I really need to be more specific and use the term moment arm. Moment arm being the perpendicular distance from the point in question to the line of action. That's your moment arm. Okay. Now, what I want to do here is I have here this slide. I actually pulled this slide from CE 312 from structural analysis, but the point is all the same. So I'm a civil engineer, and we got a lot of civil engineering students in this class, so I'll use a civil engineering example. Although it doesn't really matter, it can pretty much be anything. But I'm a bridge engineer, so this is near and dear to my heart. Here's an image of a bridge. Okay, so this is a truss bridge, and you can see we've got the abutments on either side. The trusses are sitting on the abutments, and we've got the deck. This is a 3-dimensional system. And I'd argue just about every system or physical system that we as engineers design is going to have some 3-dimensionality to it. Now, as a structural engineer, when I am analyzing that truss, I'm going to idealize that truss as what I see here on the right. Okay, so the idea is that this is a three-dimensional system, okay? But this is not. This is 2D, okay? And practically, most engineers are going to try and idealize their systems in 2 dimensions whenever possible. It makes the analysis simpler. It may be slightly more conservative, but in the end, it's a little more handleable from an analysis perspective. Now, I want to show you what that does to our moment computation. And so I think the easiest way to follow that is to look what I have here on the board. So I have here just some terms that we should be familiar with by now. So I've got my position vector and my force vector. And then the moment is r cross f. And so I can evaluate that cross product using this 3x3 determinant. And remember, I can take that 3x3 determinant and split it up using cofactor expansion into what I have here. Okay. Now, what I want to do is try and come up with a simple means of expressing moment in 2 dimensions. Okay. And so what I mean by that is I'm going to be dealing with forces and positions in only 2 dimensions. And if you remember, 2-dimensional vectors only incorporate I and j. They don't incorporate k. So maybe what I ought to do is see, well, what happens when I take these coefficients here and make them 0? What happens? Okay, so now I've taken these 2 vectors here and turned them into 2-dimensional vectors. Just some part I plus some part j. Well, so what does that do to the moment? Well, let's look at this. Well, that means this is 0 and that's 0. Okay. And so when I evaluate this out, what happens when I keep doing this? Okay, so these are zeros. These are zeros. But this one isn't changed, right? This is just x's and y's, so nothing changes here. So I've got 0 terms here, 0 terms here, nothing here. Okay, so what happens? Well, let's go back to 2x2 determinant. So if I have A, B, C, D, the determinant is AD minus BC, right? Just do the product that way minus the product that way. So what do I have here? What happens with this term? Well, I'm going to take I times the quantity that times that minus that times that. Well, this times this minus this times this, that's 0. So this is just 0I minus, what about this? This times this minus that times that. That's 0. So minus 0j. But here I actually get a term. Here I actually get a term. I get plus, and what do I get? I get Rx Fy minus Fy Rx. So Rx Fy minus Ry Fx. Okay. So I propose that if you're dealing with vectors that are only in 2 dimensions, then your moment is Rx Fy minus Ry Fx times k. Does that make sense? Here, let me get out of the way here so y'all can see that. Does that make sense? Anybody have any questions on that? And I want to, here in a second, I'm going to talk a little bit about the meaning behind this and why the formula comes out like this, what does this mean, and so on and so forth. So here, you know, this was the slide that we left off on. This is the slide, this is my following slide, and this is just me carrying that out. I kind of wanted to just do it together. I figured it'd be a little easier to see what's going on. So I propose that whenever you have a vector in 2 dimensions, what that means is whenever you have a position vector and a force vector in 2 dimensions, you're going to generate a bending moment, or a moment. I guess I should say I need to refrain from using bending moment. We generate a moment in the 3rd direction, in the z direction. Okay. The idea behind that makes it, well, first off, it's going to make our math a little easier down the line. First, okay, so let's take a look at this. So this is the formula for that vector. Now, I propose that anytime you have vectors in 2 dimensions, that the moment is always going to be in the 3rd dimension. So much so that a lot of times we actually dispense with the vector notation a lot of times in 2 dimensions. We don't even bother writing everything in IJK format. Instead, we just deal with the magnitude because it's always going to be about the z direction. And keep in mind, the ultimate definition is just going to be force times that moment arm. Now, let's see if we can glean a little bit of understanding with this, and let's see if we can also tie that understanding to the example that we're about to do. Now, so I want to talk about moments, and I want to talk about their sign convention. Okay, so moments in 2D, because I want to make a point about this. Okay, so let's say that this is the y-axis and this is the x-axis. Okay, now let's remember the right-hand rule for a second. Okay, so the right-hand rule states that if you have vector 1 times vector 2, like if we're talking about a cross product, then the 3rd vector points in the direction of your thumb. You start off with vector 1, curl to vector 2, and then this is the direction of your cross product. And the same thing works with your coordinate system, right? So this is the x-axis. I curl my finger towards the y-axis. Z points in and out of the board. So if this is the x-axis, this is the y-axis, Z is actually pointing towards you right now. Okay, and if you follow your right-hand rule, you are curling your fingers this way. Okay, in fact, you are curling your fingers in a counterclockwise fashion. Well, I propose that as a result, counterclockwise moments are considered positive. All right. Anytime that we compute moments in 2 dimensions, typically what we're going to find, and let me say this, if we use the formula that we just derived, this is always going to be the case. Counterclockwise moments are going to be considered positive. Sometimes we can get around using that formula and just use force times moment arm. And whenever you're using force times moment arm, you kind of have to be a bit careful on your direction. So typically when you express a moment in 2 dimensions, you might have a moment and it might equal something like, I don't know, 600 foot-pounds. That's a very common unit for a moment. And so there's a couple of ways we could express this. We might say 600 foot-pounds of moment that is acting counterclockwise. That's one way of doing it. Or we could also say that that's positive 600 foot-pounds of moment. Later on, when you all take me for structural analysis, you civil engineering students, a lot of times I dispense with the positives and negatives, and I just write the direction, either counterclockwise or clockwise, because I think sometimes when the problems get a little bit more intense, it's a little easier to just track the signs. But for now, we're going to try and make sure that we tie the direction to the positive and negative, to the signs. And keep in mind, you know, when we're talking about moments, moments are different than forces. So for instance, if I was talking about a force, let's say in the y direction, I might express that force in the y direction. If it's positive 200 pounds, that would be 200 pounds acting up. So remember, forces are going to act to translate. Remember, forces are actions on a system that increase its tendency to translate. So forces are going to act either up and down or left and right. Moments are going to rotate. They're going to either rotate clockwise or they're going to rotate counterclockwise. Okay? So whenever we express a moment, it's either going to be, you know, clockwise or counterclockwise or positive or negative. If you go back actually to the, I'm actually going to, let me share my screen real quick. if you go back to the example that we did last time, this was the example that we did during class on Friday, and we generated a moment vector that looked like this. But one of the things that we really didn't talk about, ooh, I forgot a little K hat on there. Look at me. Nobody corrected me on that. I'm just messing with you. We have an I hat, J hat, and a K hat, and we've got this like negative 7680 and this positive 28800 and all of this. What do those numbers mean, right? We didn't really talk about that. Well, I propose that if we're talking about, let's say, the 7680, okay, that's negative. So that is a moment acting clockwise about the x-axis. And the magnitude of that moment about the x-axis is 7,680 Newton millimeters. Foot pounds maybe in US units, Newton meters or Newton millimeters in SI units, and the negative indicates the direction. Okay, the same thing with the Y and Z. Those are positive, so they're counterclockwise moments about those axes. Again, moments tendency to rotate, forces tendency to translate. Okay, and that's why we express them as such. Okay, any questions so far? Okay, I want to take this example, and I kind of want to talk about it a little bit. This is a pretty basic example in the book, but what we're going to do is we're going to take this example, we're going to do a lot with it. So I want to, it's more about exploring a couple of things about the example. I don't want to just, here's the problem, just do it. I want to see what all of information we can glean from this. So I have a lever that's 24 inches long, and it's at some orientation, was 60 degrees from the horizontal, and it's got a 100-pound force tipped up, acting downwards at A. And so I want to explore a couple things. Let's determine the moment. Let's determine the horizontal force at A that would generate the same moment, and the smallest force that would generate that moment. Let's see if we can glean some understanding from this. So let me go to the page in the notebook. There we go. Let me take this down. Give me 1 second. Okay. So let's do a couple things with this. First off, all right, let's just keep it simple. Okay. Point O. Oh, hold on. I got to turn my pen on. There we go. Okay. So point O. Point O is the point about which moments are being taken, and we're trying to determine the moment that is generated by that force. So let me ask you a question, just making sure that chat's awake and y'all are paying attention. Is this moment going to be operating in a counterclockwise fashion, or is it going to be operating in a clockwise fashion? Clockwise, exactly right. So I propose that if this is going to be a clockwise moment, then our answer better be negative if we use the formulas, because counterclockwise moments are considered positive, so clockwise moments are going to be considered negative. So we better get the proper sign for our answer at the end. So let's compute the moment about point O. Okay. So first off, somebody look at this force vector and tell me, how would you express this force vector in IJ notation? Well, it wouldn't be so if we're talking, so I'm talking about this force right here, Miss Davis, you got it correct because it's acting vertically in the y direction. So this is going to be 0I minus 100J. And maybe I'll put in pounds. Okay, does that make sense? Yeah, it's negative, but there's no I component there because it's just a force in the y direction. Now, what about the r vector? Well, the r vector is going to take a little bit of doing because I got to look at this triangle here. All right, so this is 60 degrees, and I know that this is 24 inches. And so what I need to determine is Rx and Ry. Okay. And to be clear, I'm actually going to do this problem two different ways with sort of two different definitions of R. And I think you'll see how this is pretty straightforward. So now Rx and Ry, I mean, how are we going to compute those? Well, this is a triangle. This should be pretty simple. So Rx is going to be 24 inches times the cosine of 60 degrees, and this is 24 inches times the sine of 60 degrees. So help me out. Rx, I'll do Rx, you do Ry. So Rx, that one's easy. That actually comes up to just 12 inches. So how about Ry? Somebody help me out. There we go, 20.78. So there we go. Good deal. All right. Now, therefore, R is 12I plus 20.785 J in inches. And keep in mind, what I'm doing is I'm saying that this is the start. And this is the end, right? I mean, how do you define R? R starts at the point about which you're taking moments, and it ends at any point along the line of action. So keep in mind, I want to show you something. You know, this right here, that is the line of action of F, right? And that right there is the point about which you're taking moments. So R could be anything. It could be that, it could be that, it could be that, it could be that. It could be any one of those vectors, and you will get the same answer for the moment every time, okay? In fact, we're going to leave that up there because I'm going to try a different R here in a second, and again, you'll see you get the same answer. So therefore, if I have R is 12I plus 20.785 J, and again, that's inches, and then F is 0I minus 100J in pounds, and therefore the moment, and because we're dealing in two dimensions, I'm not even going to worry about expressing this as a vector. I'm just going to compute the magnitude of that, which is Rx Fy minus Ry Fx, which is, okay, Rx is 12, And so maybe what I'll do is I'll throw the units in. So 12 inches times minus 100 pounds minus RY, which is 20.785 inches. And then this is 0. So that on the right cancels, and then I get 12 times 100, which is 1200. But remember, that's negative 1200. And then the way that we write that whenever we write out a moment is we tend to write inches, pounds. So you can put a dash in front of it. You can put a little dot in front of it for multiplication, however you want to do that. And so we would say that's inch pounds, kind of like foot pounds, but in inches. Sometimes you'll see the book write it as pound inches. It doesn't really matter, whichever order you want. And remember, the moment came out negative, which indicates 1,200 inch pounds, and that is clockwise. Okay, just like we said it would. So negative moments are clockwise. This came out clockwise. That's one of our answers right here. Now, first off, before I skip ahead and move on to some other parts, I want to make sure that are there any questions? Is there anything that's confusing about this? Because I'm going to take this problem and I'm going to do a little bit more with it, but I want to make sure this makes sense. Can you show how to see clockwise? Great question. And so here's how I would draw that. Okay. Here's point O right here, and then we have a force acting like this. And so the way that I would imagine this is, imagine that point O is kind of like a steering wheel. Okay. Imagine that there's kind of like a steering wheel around point O. If you took that 100 pounds and put it on the steering wheel like that, how would that turn the wheel? It would turn the wheel clockwise. Does that make sense? And so that's how you would tell if it's clockwise. If 100 pounds was going upwards, it would be counterclockwise. Or if the 100 pounds was on the other side of point O, that would be how you would determine. That's, yeah, great question. Now I'm going to kind of cheat and use this this image a bit. I want to ask a question. So actually, I'm going to erase all this because I want to redraw something here. Okay, I want to show you an alternate definition of moment about point O. And admittedly, when we get later on into the class, when we start looking at, determining support reactions and drawing shear and moment diagrams and truss analysis and all this stuff, we're pretty much going to be using this alternate definition much more commonly. And so I really want to give this its attention. The alternate definition is what we had in the slides, which was just F times D. Okay. Now, F is the magnitude of the force vector, which in this case is just 100 pounds. Okay. Now, D is what we call the moment arm. Okay. And the moment arm is the shortest distance from point O to the line of action of F. Okay? So let's go back to my example. Okay, so this is point O, and there's some lever like this going through point O, and right here is the 100-pound force. Okay, now this 100-pound force, again, let's draw up that line of action. That line of action extends up and down forever. Okay, and so my question for you is, what is the shortest distance from point O to the line of action of F? Like, how do we draw the shortest distance? Go back to, your algebra or geometry classes. What is the shortest distance from a point to a line? And it's the perpendicular distance. And Mr. Brown, dead on. So it's this distance right here. That distance is D. And so did we already figure out D up here? And the answer is yes. We figured that out. D in this case was Rx. And so Rx was 12 inches. So therefore, moment is force times distance, which is, or force times moment arm, inch-pounds. The one disadvantage to doing it this way is when you use the Rx Fy minus Ry Fx, when you use that formula, the math sort of takes care of you having to figure out whether or not it's a positive moment or a negative moment. But when you use the F times D formula, you kind of gotta just make sure that you don't forget to indicate that that's a clockwise moment. Because here's the thing, a 1,200 inch-pound moment doesn't really mean much without its direction. You need to know that that moment is expressed in a clockwise fashion. Otherwise, it doesn't really mean much. Same thing with a force. 200 pounds is great, but I need to know whether it's 200 pounds going up or down or left or right or whatever. Any questions moving forward? Because I got a little bit more I want to do. Okay. Let's talk about this next question. So the next question is, what horizontal force applied at A would generate the same amount of moment? Okay, so let's see if we can figure that out. So here's that point O again. Here's the lever. All right, and what we're trying to do is figure out what force would generate a moment of 1,200 inch-pounds. Well, there's a couple of ways of going about this. You could use the formulas, right? You could say that F equals sum Fx times I plus 0j, and then use your R vector, and then try and set up an equation and solve. I want to keep this a little simpler. All right, let's see if somebody can help me out with this. What is D in this case? Yeah, you're right on the track. Yeah, Mr. Hale, you kind of stole it for me a bit. What is D? So it's RY, which is, and what was RY? Remind me. $20.785 inches. Don't forget units. So if moment is force times the distance, and we have, I'll need the parentheses over here. Moment, I know I want 1,200 inch-pounds equals a force, which I don't know, and then a distance, which is 20.785 inches. What value of F do I need? £57.7. Do I have a second on that value? There we go. And you're exactly right. Exactly right. Now, all right, any questions before we move on to this next thing I want to look at? All right, let's look at this next one. This next one seems hard, but it's actually really easy. All right. What's the smallest force that you could apply at A to generate the same moment? And I'll tell you, this one, it looks harder than it really is. And let me explain why. So what's the hardest force you could, or the smallest force you could apply at A? Not hardest. Okay. So here's the point. Here's the lever. Okay. And what I want to do is I want to generate that 1,200 inch-pounds moment about this point O. Now, let's go back to the wrench example. Remember when we were first starting to talk about wrenches, and I said, okay, if you have a wrench sticking right here and you want to apply a moment, okay, there's a way in which you would yank the wrench in order to be most effective, right? You don't take the wrench and you pull it, you pull it perpendicular, right, to the axis of the wrench. In other words, if I want the most effective force, I need to pull that wrench that way. Okay? So I need to know what the magnitude of this force is to where I can generate a 1,200 inch-pound of moment. And, you know, I'm sure some of you are thinking, hold on, I got to take this. Okay, so this is an angle, so I need an Fx component plus an Fy component, and thinking, oh, God, this just looks nasty. It's not. It's not. And I promise it's not, because I can use this definition. Okay? What is the moment? The moment is 1,200 inch-pounds equals some force times some moment arm. So what's the moment arm? The moment arm is the perpendicular distance from the line of action of the force, there's the line of action, to the point. And so what is D in this case? 24, exactly, 24 inches. Because that's how long the lever is, so 24 inches. So therefore, F is what? There you go, 50 pounds. All right, so help me out. I don't think this is too bad. Anybody have any questions about this? While you're working on that, I'm going to pull something up. Questions? I got something I want to show you. Let me see if this showed up in my OneDrive. I want to show you something for tomorrow, or sorry, for Wednesday if I can. Okay. Here we go. All right. What we're going to do next time is we're going to, and I'll go through the derivation. I don't really want to spoil that for Wednesday, but we're going to do a little bit more of a general expression of what we did today, which is how to determine moments about any axis. See, what we did today is we did moments in 2 dimensions, but really another way of saying that is we determine moments about the z-axis, okay? And that's what moments in 2 dimensions are. They're always moments taken about the z-axis, the one normal to the sheet of paper that you're writing on. If this is the x-axis, this is the y-axis, they always go normal to that. Well, instead of taking moments normal to just the z-axis, what if I took moments normal to any axis? Okay. Well, in order to do that, we have to use the second of 2 ways of multiplying vectors, and that's to use what's called the dot product. Now, I'll go ahead and not really forewarn you, it's the opposite. Cross products were involved. There was a lot to a cross product. Dot products are easy. They are really easy to compute. They're about the easiest vector, or about the easiest computation that we do this entire semester. If you have vector 1 and vector 2, you can do the dot product in a matter of seconds. So we're going to talk about that next time, and really what we are going to try and figure out is what is the moment about any arbitrary axis. And once we've figured that out, I think we've pretty much figured out how to take a moment about a point. And then what we're going to do is start to use that concept. We're going to use it to break down some force couples and use it to break down some rigid body systems. And with that, I think I'm going to go ahead and call it for today. Tomorrow we'll delve into what is the derivation of the dot product. I'll go ahead and show you the spoiler alert. This is the answer right here, this thing down here on the bottom. All you do, if you have vector 1 and vector 2, you just take each of the numbers. You take the x coefficients, multiply them, the y coefficients, multiply them, the z coefficients, multiply them, and just add them together. And that's the dot product. It's really, really easy. And then we can take that concept to determine moments about an arbitrary axis. But we'll discuss that on Wednesday. In the meantime, you all have a homework assignment that's due Wednesday that's very similar to today. I'm giving you a situation and asking you to compute the moment about a point, and then a bunch of other stuff related to that. That's all I have. I will see you all on Wednesday.